Hi everyone. In this video, we are going to talk about the factor theorem. It is kind of an extension of the remainder theorem. There's a separate video on remainder theorem. For factor theorem, the theorem says that if we have a polynomial, suppose you have a polynomial p of x, and it is divided by one of its factors, let's say x minus c. This is a factor. So we are dividing the polynomial by one of its factors. If we do that, then the remainder which is actually p of c, it must be 0. That's what the factor theorem says, right? If a polynomial is divided by one of its factors, then the remainder p of c will be 0. Now let's take a few examples and understand what a factor is and what happens when you divide a number by one of its factors. I'm going to take some simple arithmetic example, right? Let's say suppose we have a number 15. Let's take number 15. So what are its factors? If we do prime factorization, it would be 3 times 5. So 3 is a factor of 15. Also 5 is a factor of 15, right? So if we divide 15 by 3, one of its factors, 3 goes 5 times, and we are left with no remainder, meaning the remainder is 0. As you can see, we are now left with a remainder 0. And then also if we divide 15 by its other factor, which is 5, it goes 3 times into 15, and then also we are left with a 0 remainder, right? The remainder is 0. Now let's take another example. Suppose we take maybe, let's say 12. Well, 12, if we do prime factorization, it would be 2 times 2 times 3. So if we divide 12 by one of its factors, let's say we divide by 2, well, 2 goes 6 times into 12. That leaves no remainder, that means 0 remainder. And similarly, if we divide 12 by its other factor, let's say 3, and 3 goes 4 times into 12, so here also no remainder. I mean, the remainder is 0. So from these examples, we can clearly see that when a number is divided by one of its factors, it leaves no remainder, meaning the remainder is 0. In other words, if we say that when a number is divided by another number and it leaves no remainder, then the divisor must be a factor of the dividend. So now let's write it down in a formal way. So we are going to write it as like this. So we'll say, okay, if p of x, we'll say if p of x, a polynomial that has a degree, suppose it has a degree greater than or equal to 1, it cannot be a constant polynomial. It must be at least of 1 degree, at least degree greater than or equal to 1. So that kind of a polynomial it is. So if this polynomial is divided by a factor, meaning one of its factors, right? By a factor which is x, a linear factor, of course, a linear polynomial, x minus c. So let's assume that x minus c is a factor of the polynomial. Then p of c will be equal to 0, and p of c is nothing but the remainder. When p of x is divided by x minus c, p of c is the remainder. I have done a whole video on this, on the remainder theorem. You can watch it to understand why p of c is the remainder. But p of c will be the remainder when p of x is divided by x minus c. Now let's take a couple of examples. So suppose okay, so let's do an example, right? So first we are going to take an example. Say suppose we have been given a polynomial. Let's say it is p of x equals let's say x squared minus 2x plus an unknown constant c, suppose, right? And then we say that x minus 1 is a factor. So we are saying that x minus 1, this is a factor it is a factor of the polynomial, then find the value of c. Find the value of c. That's the question. So we have a polynomial and x minus 1 is a factor of the polynomial. Find the value of c. Well, if x minus 1 is a factor, that means if the polynomial is divided by x minus 1, the remainder must be 0. Now, from the remainder theorem, we know that when a polynomial is divided by x minus c, so from the remainder theorem, it's like this. If a polynomial is divided by x minus c, then it gives a remainder. It gives a remainder which is equal to, let me write it down. Remainder is equal to p of c. And from the factor theorem, we are saying that the p of c must be equal to 0. So when x squared minus 2x plus c is divided by x minus 1, it is going to leave a remainder of p of 1, because if you see right here in the remainder theorem, this c and this 1 right here, they are equivalent. We are going to divide the polynomial by x minus 1, but in the theorem we divide it by x minus c. So this c and the 1, they are kind of equivalent. So wherever we have c, we are going to use 1 for this particular example, right? So now let's continue with the example. So if p of x is divided by x minus 1, the remainder will be p of 1. So p of 1 must be equal to 0. That's exactly what the factor theorem says, that if you divide a polynomial by one of its factors, the remainder will be 0. In this case, we are dividing by x minus 1, which is a factor. That's a given information, right? And if we divide by x minus 1, then what will be the remainder? Well, the remainder will be p of 1. And from the factor theorem, because we are dividing by one of its factors, the remainder must be 0. That is our required condition, right? And then let's try to evaluate. So from here, we are going to say, okay, so what is p of 1? Well, p of 1 will be the value of the polynomial when x is replaced by 1. So let's replace x by 1 in the original polynomial. The original polynomial has x squared. So instead of x squared, I am going to write 1 squared minus 2 times x. So this is 2 times 1 plus c. So wherever we had x, I am substituting that by 1, because we are trying to evaluate the value of p of 1, right? So then this must be equal to 0, because that's exactly what we have here. P of 1 must be equal to 0. That means this must be equal to 0. So from here we can say, okay, so 1 squared is 1 minus 2 times 1 is negative 2 plus c must be equal to 0. And from here we can say that c, let's keep c on the left hand side, and then let's transpose everything to the right hand side. So it would be negative 1 and positive 2, that is equal to positive 1. So we found the value of c, so hence we can say c is equal to positive 1. Let's take another example. Suppose we are given a polynomial. So this is another example. Suppose we are given a polynomial which is p of x is equal to, let's say, x squared minus 3x plus some unknown constant k, right? And we have been told that x plus 1 is a factor. The question here is we have to find the value of k, right? So what is provided here? Well, our solution would be, so let's do our solution. And we have been given the polynomial which is x squared minus 3x plus k, and the factor is one of its factors has been provided as x plus 1. Well, we need to somehow write this in form of x minus c. So if I have to write x plus 1 in form of x minus something, I can say x minus negative 1. So negative of a negative 1 becomes positive 1. So x plus 1 is essentially equal to x minus negative 1. Now this negative 1 can work as the c as in the theorem, right? So now let's try to find out the remainder, because if we divide this polynomial by a factor which is x plus 1, the remainder should be 0. Now in this case, what is the remainder? The remainder is p of c. In this case it is p of negative 1. That's the remainder, because remainder is p of c, and here c is equivalent to negative 1. So this is our remainder and this must be 0. That's the required condition from the factor theorem, right? Now let's try to evaluate the value of p of negative 1. So p of negative 1 will be the value of p of x when x is equal to negative 1. So hence we can say that p of negative 1, so wherever we have x, we are going to replace that with negative 1. So we had x squared, I am writing negative 1 squared, minus 3 times x, so I am going to write it like this, 3 times negative 1 plus k, and that is equal to 0. That's our equation, right? So from here we have to solve for k, and that's going to be pretty easy. So from here we can say that negative 1 squared is positive 1, then negative 3 times negative 1, that's positive 3, plus k is equal to 0. And from here we can say, okay, 4 plus k equals 0. From here we can say k equals negative 4. If you transpose the positive 4 onto the right hand side, k equals negative 4, and that's the solution, or that's the answer here, right? So if x plus 1 is a factor of this polynomial, then k needs to be negative 4. Now if we use negative 4 in place of k and then do a quick division, let's do the quick division right here. So the polynomial is now going to look like x squared minus 3x, and then k has a value of negative 4, so I am writing minus 4 right here, and let's divide that by x plus 1, and I want to see if it is going to leave any remainder. It should not. If x plus 1 is a factor of this polynomial, there should be no remainder. The remainder should be 0. So let's try this division and see what happens. So x goes x times into x squared. So I write x in the quotient and then x squared here, and then x times 1, that is positive x. And let's change the sign here. This becomes negative, this also becomes negative, this is going to cancel out each other, and we are going to be left with negative 4x here, and then negative 4. Now x goes negative 4 times into negative 4x, so I put negative 4 in the quotient, and then it would be negative 4x, and 1 times negative 4 would be negative 4. Alright, beautiful. So now we're going to change the sign and sign. Now this is going to cancel each other, and this is also going to cancel each other. So essentially we are left with 0. So you see our remainder is 0. Our remainder is 0, exactly what we expected. That if x plus 1 is a factor of x squared minus 3x minus 4, then if we do the division, the remainder better be 0, and we have proved that yes, it came out to be 0. So that means our factor theorem is working. I hope everything made sense. Thank you for watching. See you in the next video.